called the polar covalent bond. So, pag sinabi nating non-polar covalent bond, so nag-exist ito between similar atom. Similar atom, paano yun? So, let's say for example, nitrogen and nitrogen. So, yun. So, pag syempre pag nag-combine at nag-bond yung dalawang atom na yun, so it form compound at yung kanilang sharing of electrons ay tinatawag nga natin na covalent bond. And usually, sa covalent bond, dito sa non-polar covalent bond, electrical charges are uniformly distributed. And of course, they are symmetrically oriented. So, let us have this example. Okay, so sharing, wala na tayong transferring ngayon. So, sharing na. So, let's say for example, so let us have N2 or the nitrogen gas. So, syempre, ang una muna natin kailangang malaman is ano ba ang kanilang valence electron. So, alam naman natin na ang nitrogen ay meron siyang valence electron na 5. Dahil nanggaling siya sa 1s2, 2s2, okay, 2p3. Okay? So, kung ating titingnan, ano ba ang kanyang outermost electron? So, first energy level, so hindi na ito. Second energy level, at siya ang nasa outermost. 2 plus 3, that is 5. So, kaya ang ating valence electron is 5. So, paano natin ipapakita ang kanilang sharing of electron ng ating nitrogen gas? Okay, so ulitin natin. So, nitrogen gas. So, ilan ang kanyang valence? 5 ang valence electron. So, N. Okay, 1, 2, 3, 4, 5. So, yung isa pa, so dahil isa pa lang yan, dahil tayo N2, nitrogen gas, so another N ulit, another nitrogen, 1, 2, 3, 4, 5. So, ilan ang kailangan niya para maging stable ang configuration? Anong sabi natin? 8, 8. So, kung may 5 na siya, kailangan pa niya ng 3. So, saan manggagaling yung 3 para maging stable siya? So, syempre, kaya nga sa covalent bonding ay sharing of electron. So, pag share niya itong isa sa kabilang nitrogen na electron, so, ilan na siya? So, naging 6 na kasi share niya. So, yung kabila, dahil nakishare din siya, meron na rin siyang 6. Share niya ulit yung isa pa. Yan. So, 6 na ulit, 7 na. Pag shinare niya pa itong isa, at shinare din niya yung isa, so, 8 na. So, pag binilang natin yung kanyang electron, 1, 2, 3, 4, 5, 6, 7, 8. Kompleto? Yes! How about the other one? 1, 2, 3, 4, 5, 6, 7, 8. So, yan. So, ito na magiging itsura niyan. So, mapapansin nyo, meron tayo, ayan, ito na nga. Ayan. So, this is the covalent bonding of nitrogen gas. How about if it is oxygen gas? Okay. So, ang oxygen ay meron siyang 6 na, what do you call this? Meron siyang 6 na valence electron, di ba? So, since dalawang oxygen yan, so 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so saan manggagaling? 6. Ilan ang kailangan? 2. So, sabihin, mag-share ulit siya dito at mag-share ulit siya sa kabilang oxygen. So, if we count the number of electrons, 1, 2, 3, 4, 5, 6, 7, 8. And then, sa kabilang side, 1, 2, 3, 4, 5, 6, 7, 8. So, di ba, na-achieve na niya ang kanyang stable configuration. So, yan ang ating covalent bonding. And kung mapapansin niyo, yung example natin kanina ay nitrogen gas, and then the other one is oxygen gas. So, let us have the polar covalent bond. So, usually kapag polar covalent bond, it exists between dissimilar atoms. So, magkaibang atom naman sila. And of course, the electrical charges are not uniformly distributed and they are asymmetrical. So, let's say for example, let us have the boron trifluoride. So, ang boron ay meron siyang valence electron na 3 and ang fluorine ay meron siyang valence electron na 7. So, pag ito-drawing natin siya, so ang ating fluorine ay may 7. 1, 2, 3, 4, 5, 6, 7. So, ang ating boron naman is mayroong 3. 1, 2, 3. Okay, and then, so syempre, kung merong isa dito at shinare niya dun, so ayan, tinignan natin, okay, this is the, yan. And then, another fluorine, dahil tatlo yung fluorine, so, 1, 2, 3, 4, 5, 6, 7. So, share natin. And another fluorine, 1, 2, 3, 4, 5, 6, 7. So, ganyan yung structure niyan. So, bilangin natin kung 8 na nga talaga. So, sa fluorine, tingnan nga natin kung naging stable siya. 1, 2, 3, 4, 5, 6, 7, 8. So, this is 8. So, kompleto. How about this one? 1, 2, 3, 4, 5, 6, 7, 8. Kompleto din, 8. So, how about the other one? 1, 2, 3, 4, 5, 6, 7, 8. So, ayan. Siya din ay kompleto. So, 8 din. And yung mga polar covalent bond ay pwede rin siyang maging non-polar covalent bond if bonds are equivalent and symmetrically oriented. Example, uh, okay. So, example itong CH4. So, yung CH4 ay, syempre, kung titignan nyo, meron tayong isang molecule ng carbon and 4 molecules of hydrogen. So, this is considered as non-polar kasi ano ba ang kanyang valence electron? Ang valence electron ng hydrogen is 1 at ang valence electron naman ng carbon is 4. So, pag drenowing kasi natin siya, okay, so pag drenowing natin siya, so, isa, dalawa, tatlo, apat. So, ang valence electron ng carbon is 4. 1, 2, 3, 4. So, pag ating kinonect siya at transfer, shinare natin siya. So, ayan. Pag shinare natin siya, so, pag binilang natin, ilan na ngayon ang electrons ng carbon? 1, 2, 3, 4, 5, 6, 7, 8. So, naging 8, stable na siya. And yung hydrogen, sadya namang, ayan, 1, 2, yan. So, pag binilang din natin siya, meron din sa hydrogen. So, ang hydrogen naman is isa lang ang valence electron. Yan. So, kung mapapansin nyo, they are symmetrical. Symmetrical, pag sinabi natin symmetrical, the molecular shape has equal angle. So, ito yung tinatawag natin na polar covalent bond may become non-polar covalent bond if the bonds are equivalent or symmetrically oriented. And then, lagi niyong tatandaan na many covalent bonds are gases. So, sila ay mababa ang density and they are weakly attracted to one another.
Hydrogen bond. To answer this question, we have to start from the basics. You cannot form a hydrogen bond with any hydrogen. H has to be bonded to F, O, or N. These are very electronegative elements. Hydrogen is bonded to any of them. These guys will draw the electrons to themselves. Very large electron cloud on the fluorine and very little electron cloud on the hydrogen. Strong partial positive charge on the hydrogens will develop. You need a lone pair of electron on F or N. A lone pair is a high electron density reason. The fluorine also has electrons which are just hanging around, meaning even stronger partial negative charge. Strong partial negative charge, strong partial positive charge, strong IMF.
The covalent bonds between atoms are quite strong, but the intermolecular forces, or the attraction between molecules, can be relatively weak. The addition of a small amount of energy separates these molecules easily. Therefore, they have low melting and boiling points. Ionic compounds dissociate into ions when dissolved in water, and ions conduct electricity. On the other hand, covalent compounds separate into molecules rather than ions when dissolved in water, so it typically does not conduct electricity. Covalent molecular compounds can be polar or nonpolar. The polarity of molecules results from the differences in the electronegativity of the bonded atoms. Electronegativity is the ability of an atom in a molecule to attract shared electrons toward it. The greater the electronegativity of an atom, the stronger is its ability to attract shared electrons towards itself and away from the less electronegative atom. The electrons are not shared equally, and part of the molecule carries a partial positive charge, while the other part carries a slight negative charge, creating a dipole. For instance, the covalent bonding between hydrogen and fluorine. Fluorine has an electronegativity of 4.0, while hydrogen has an electronegativity of 2.1. Thus, fluorine is more electronegative than hydrogen, and so the shared electrons spend more time around the fluorine atom, creating a partial negative charge. This kind of bond is a polar covalent bond. When two identical atoms covalently bond with each other, like two atoms of fluorine, there would be equal sharing of electrons between the fluorine atoms. This type of bond is a nonpolar covalent bond.
So take, for example, calcium chloride. We know that calcium is Ca and that chlorine, the chloride ion, that's Cl. So we have CaCl, but because this is an ionic compound, we have to take the charges into account. So if we look at the periodic table, this one's set up to show us the charges, we can see calcium right here is in group 2, so it has a 2 plus ionic charge. The chloride ion, that is right here in the halogens, that has the 1 minus ionic charge. So for this to be a valid formula, these have to add up to 0, have a net charge of 0. So let's use the crisscross method. We can take this 2 plus here and move it down here, and we can take this 1 minus and move it over here. We don't leave the charges in, so let's get rid of those. And we don't usually write 1, that's assumed. And that's the formula for calcium chloride using the crisscross method. So now you try one. Pause and write the formula for aluminum bromide. So for aluminum bromide, we have Al and then Br. We said the aluminum, that's 3 plus, and the bromine is 1 minus. So let's crisscross them. We'll take the 1 minus and move it down here. We don't write the minus, so we'll get rid of that. And actually, we don't write the 1 either. And then the 3 plus, we move that down here. Let's get rid of the plus. And the formula for aluminum bromide is AlBr3.
P4S10. Okay, for the first element, we'll start with the element name. P is phosphorus. If you didn't know that, you could look it up on the periodic table. For the second element, that's S here, start with the IDE name. So S is sulfur, and its IDE name is sulfide. Okay, so those are the two names. Now we're going to use prefixes to show how many atoms of each type we have. We got P4, so that means we have 4 phosphorus atoms. So 4 is tetra. We use the tetra prefix. Tetra. And then for sulfide, we got 10. So we'll use this prefix, deca. Deca. So the name of this compound is tetraphosphorus decasulfide. Let's move on. We're going to add a couple more steps to deal with more complex formulas. PCl5, let's name this. So P, the first element, is phosphorus. Cl, the second element, is chlorine. And chlorine's IDE name is chloride. So there it is. Now, we get to the prefixes. Phosphorus here, we only have one of them. So we're not going to use mono here. We're just going to keep it as phosphorus. And chlorine, we have 5 of those. So we're going to use penta here as the prefix. So it's going to be pentachloride. And phosphorus pentachloride, not monophosphorus pentachloride, just phosphorus pentachloride is how we name this. Now there's one more step that we're going to add. I'm going to talk about that next. P4O6. So the P, phosphorus, is our first element, and then O, we got oxide. That is the IDE name for oxygen here. All right, now let's use the prefixes. Switch to our prefix table here. We have 4 phosphorus, so we're going to use the tetra prefix, so tetraphosphorus. And then for oxygen, we have 6 of those, so we're going to use hexa here. And just as before, we end up with this awkward name, hexaoxide. We get an AO, so we're going to get rid of this A here. Shoop. Oh, I always knock that name out of the way. Hexaoxide, and that turns it into tetraphosphorus hexoxide. You know, I forgot to circle the name in the last one, and this is just so satisfying. So I did it really slowly to make up for the fact I didn't circle the last one. So we get rid of this. We get rid of this A here. Tetraphosphorus hexoxide. So